So welcome back to this second of our two seminars this afternoon. We're extremely happy to have Benjamin Sudakov here. He's going to give us the very first real board talk of this seminar series. We're very excited to see how it works. You may want to pin his video in order to make it be big, but hopefully if you have it zoom in speaker view, that should be what you're seeing anyway. And without further ado, I'm going to hand over to Benny.
Thank you very much. I'm happy to kind of see that all you are zoomed here. So I thought that it would be indeed a bit fun to try to kind of go back to our roots and try to have, despite the difficult times, a talk on a board, how we used to do it. So I will talk about joint work with Tran and Matija Bucic, who is a brilliant PhD student we have here in Zurich. And by the way, Matija would be on the job market this year, so if you have a job, so please keep in mind this name. So he's really excellent. So I will talk about Ramsey theory. So let me start by saying that Ramsey theory belongs to a large body of deep results in mathematics, which all have, whose philosophy can be captured succinctly by the phrase, complete disorder is impossible. Also, if you look what's going on around us today in the world, and why we're sitting here zooming in my talk with this coronavirus pandemic, I don't think you would totally agree with this phrase, right? But nevertheless, in mathematics, these principles appear in high generality. Now, when you talk about Ramsey's theory, the first theorem which comes to your mind, the first statement, is the theorem of Erdős and Szekeres from 35, which says that every sequence of n-1 square plus 1 numbers contains a monotone subsequence of lemma. So let me give you a proof by example of this theorem, just to remind you why this is true. So let's look on the numbers, for example, 10, and then 7, and then 8, and then 9, and then 4, 5, 6, and then 1, 2, 3, right? So I have 10 numbers here, so I'm expecting to see a monotone subsequence of length 4. So what I can do is the following. I start with the last number, and I write below it what is the longest monotone subsequence I can get starting with this number. So obviously here is 1, and here is 2, and here is 3, and then here is again 1. From 6 I can only have 1, and then here is again 2, and then here is again 3, and again 1, 2, 3, and again 1. So if during this process I ever would have get lucky and I would see number 4, that means I would found a monotone increasing subsequence of length 4. But because I have only numbers from 1 up to 3, and there are 10 numbers, I would get some number, in this case number 1, at least 4 times. So because the way I was constructing this green subsequence, this will tell me that the corresponding numbers below which I wrote 1, they stand in decreasing order, right? So that's the reason why the result of Erdős and Szekeres is true. So this is a really famous result, and because of that, it has many extensions and also generalization to high dimensions. So there are various generalization to high dimensions. I mentioned just some name by Fishburn and Graham, by Kruskal, by linear thinking, and Sabo and Tarbush. So in my opinion, one of the most natural of this generalization is the one by Fishburn and Graham, and this is the generalization I'm going to talk about. So first of all, let me tell you what I mean by monotone two-dimensional array. Right? Again, I start with example. So let me give you the example of such array. So here is an example of such array, and then I'll tell you what to look at. So you look on this array, and you look on all rows of this array, and every row is written in increasing order, right? So you see here is 1 to 6, 3, 5, 7, 4, 8, 9. And then for every column, you look on every column, and also every column is increasing. And it's important that all rows are monotone, and columns are monotone, and rows are monotone exactly the same way. And also the columns are monotone exactly the same way. Now, obviously, it doesn't need to be necessarily always increasing. So for example, let's look on this array, just to give you a slightly different example. 3, 5, 2, 7, 4, 1. So now every row is actually monotone decreasing, but you see all rows are decreasing. They all behave the same way, and every column is still monotone decreasing. So this is what I mean by monotone array. Let me give you an example of something which I don't count as a monotone array. Also, it's very close to be such. So let me look on an array which looks like this: 7, 6, 1, 8, 5, 2, 9, 4, 3. Right? So here you can observe, right? Let's look on these two rows. Despite the fact that they all both monotone, this row is increasing and this row is decreasing, right? So they're not monotone in the consistent way. Now, why I don't want to look on such an array? Because if you remember, the theme of Ramsey's theory is that we can always find one of the finitely many configurations. Now, if I allow to my array to have rows and columns which are monotone, but not in consistent way, if I go to a bigger array, so if I look on an array n by n, then I actually can see exponentially many patterns in n, and it's important thing it grows with them, which is completely against the philosophy of Ramsey's theory. So we will come back to these arrays later, but so far for me, monotone array is an array whose rows and columns are monotone, and rows are monotone the same way, and columns are monotone the same way. So let me give you this definition on the board, right? So that we will have it for the record. So first of all, for me, d-dimensional array would be I take a d-dimensional grid. So d-dimensional grid. And I assign to every, so this is an array, right? I assign to every point of this grid a number, right? So this is the first thing. So this is how I think about array. I say array monotone if for every direction, for every I, all one-dimensional arrays in direction I are monotone same way. So this is for me monotone array. So this is a notion of Fishburn and Graham. And now following this direction, I can define you like we usually do in Ramsey's theory, the Ramsey function. So it would be m dn. It would be a minimal n such that any d-dimensional n times n, right? So if you take d-dimensional array with size big N, any such d-dimensional array has monotone n times n subarray. This is a usual thing. And the question which you obviously want to ask, how, first of all, whether this function is finite or how fast it will grow as a function. Right? So again, so I take big array and I want to find inside a large monotone array. And monotone for me means all rows are monotone the same way and all columns are monotone the same way. Okay? So this is the problem I will start with. And so let me tell you what was known about this problem before I'll tell you what we proved about this problem. Good. So first of all, let's look on the theorem of Erdős and Szekeres, which I mentioned. So this theorem says that m1 of n is n minus 1 squared plus 1. I actually forgot to mention that this is a type result. There is an example which shows that if you take only n minus 1 square, sequence of length n minus 1 square, you will not have monotone subsequence of length. So we know this thing, so this is the first result. The next result is a very simple lower bound, which you can get using a standard probabilistic approach. Right? So we know that the size of the array, which you need to find a monotone subarray of size n, is at least exponential. Right? So actually, it's at least n to the power some constant n to the d minus 1, where d is a dimension. Okay, so let me just sketch you a proof. Right, the proof is not very difficult. So let's look on the dimension. I will do dimension. Let's do dimension 2. Let's take my big N to be n to the power n of 2. Then I take my array, which is n by n array, and I put every entry to be a random number xij, which uniformly at random, right? So I use real numbers, uniformly at random from 0, 1. So this is the way I construct my array. Now you can use a simple expectation to see that the expected number of monotone n by n arrays here is, I first choose n rows, then I choose n columns. But after I decided on rows and columns, right, I have here n by n guy, right? So even if I just look on the rows of this array and I want them to be monotone, because it's a random numbers, the probability of this is the probability of having a monotone permutation is 1 over n factorial. So, and then I need this to happen at least n times. Right? And if you put this, maybe let's put it here n over 3, this is definitely much smaller than 1. And therefore, I don't expect to have a monotone subarray in this example. Right? And this works for higher dimension as well. Any questions? So now let me tell you some positive results. Right? So far, right, this was Erdős-Szekeres, this was a very naive lower bound. So Graham, Fishburn and Graham actually proved that this function is finite. And so what they managed to prove is that if you take 2 dimensions, then in order to get monotone array with side lengths n, it's enough to take big N to be a power 5 of n. Now let me remind you what is a tower. Tower is, if I put here 5, it means I need to take 4 exponentials of n to get this number, right? So the tower is a recursive function, which is defined as tower k plus 1 of x. It's a 2 to the power tower k of x. So tower 5 means it's x, 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 x of some constant function. Right? So this is for 2-dimensional arrays. And then it gets much, much worse if you go for d-dimensional arrays where d is at least 3. So what they showed is that this is at most Ackerman function. I will not even go into definition of Ackerman function. For people who don't know, this is an extremely fast-growing function which people first discovered in logic, which goes faster than tower of tower. So this is a really huge number. Okay? So that's what they proved about the thing, that it's finite, but if you want, if you're realistic, it's very finite, right? It grows, so their bounds grow very well. Right. So the first result which I want to present here is an improvement of these bounds, right? We managed pretty substantially improve these results, and that's what I'm going to talk about. So actually we'll keep definition for you if some people came later, and I will just, right, so the main moral was to remember that the bound was mostly Ackerman before, and let me show you what we can prove now. The theorem, this is, as I said, Bucic, myself, and Tran. So let's start with the 2 dimensions. So to get a 2-dimensional monotone array, we showed that you need to take big N to be at most double exponential. Actually, you'll see in this talk, I will have some low-order terms everywhere, but in order to write the result nicely, I'll write it like that, but actually we need 2n times 1 plus epsilon, but you will see from the code, right? So this would not be important. Then we manage also to show that double exponential enough, even in 3 dimensions, right? We have at most 2 to the 2n squared, right? It's still double exponential, but now the exponent is in square. Unfortunately, you will see from the proof, I mean, this is a really special case. I will not talk about it. It requires certain tricks. Unfortunately, these tricks only worked in 3 dimensions for us. We didn't manage to push them further, but we found some other tricks which actually worked always. And so what we managed to prove, on expanded value extra exponential, you can do all the dimensions, right? So for 3 and more dimensions, actually for 4 and more dimensions, right? Let me write 4 because 3 we already did. We know how to prove 2 to the 2 to the 2 to the n to the d minus 1. So triple exponential, right? Instead of double exponential, triple exponential. So these are the new results. The first batch of new results. I will mention something later I want to talk about. Okay. So I want to talk about some ideas of the proofs of this result. Actually, the proofs are not bad. The proofs are not technical or extremely involved. Like usually in Ramsey's theory, right? You need to look on the things in the right way. Once you have a right way, you get result relatively succinct. Okay. So let me start with this bound because this would be very simple to explain. So I want to show again, right? What is my goal? My goal is to find a big array, 2-dimensional, right? So I have a big N by big N array, and I want to find small n by small n subarray, which is monotone, which means all rows are monotone the same way, and all columns are monotone the same way. Okay. So again, let me start with my n being 2 to the 2 to the 2n. Right? And instead of looking on the full array n by n, I will look on a one long strip. Right? So this would be my first picture. Right? So I look on the strip of this array. So the length of the strip is n, but the width of the strip would be 4n squared, which is 2n squared. So this would be what I look. So now you can guess already from the numbers which I'm giving what I'm going to do. So I look on every column, vertical column, say position I, right? And because the length of this column is 2n squared, by using usual Erdős-Szekeres, I can find here, right, a subset Ri, right? So this Ri would be of length 2n, and the indices which corresponds to Ri would be monotone. Right? So I can find in this column a subset which forms a monotone sequence. Now, because the number of positions of arrays at most 4n squared choose 2n, I would know that many such arrays would be in the same position. So I would have that there are at least n divided by 4n squared choose 2n. But observe, this is only exponential in n. This is double exponential in n. So losing nothing. So with slight abuse of notation, I write that this is really back n. So I have that many indices I such that array are the same. By the same, I mean same location. Okay. Good. So now I can take this problem and then I reduce it to the following simple problem, right? So now I have still my very long strip. So here I have n. Here I will have already 2n. And I know that these vertical guys, they monotone. So every column is monotone. Right? So now I look on the first row of my array, right? Look on the first row. In first row, find, again using Erdős-Szekeres, find a set C1, right? Let me draw it right here. So this is C1. C1 would be of size roughly square root of the length of the row, right? Because Erdős-Szekeres, you always pay square root, such that C1 monotone. And then you look only on these indices in C1, and you go to the second row, and you find in the second row C2, right? So then find C2, which I'll write with a slight abuse of notation, which is subset of C1. I don't mean it's subset because it's in the second row, but it's a subset of the indices of C1, right? So I can find here C2, such that C2 is the size of C1 again, square root, such that C2 is also monotone. And then continue doing this. So at step I, you find Ci plus 1, which was subset of Ci, such that Ci plus 1 has, again, right? So you continue doing this and you get C3 until you get to the very end, which is C12. So Ci plus 1 is Ci square root, which is exactly your n. So C1 was to the power half, C2 to the power quarter. So this would be 1 to the power 2i plus 1. Right? And since my n was double exponential in 2n, I can do this procedure 2n. And in the end, right, I will finish, right? So what will be the end outcome of my thing? I will have this block of size 2n, 2n, where every row is monotone and every column is monotone. But maybe not the same way. Now in 2 dimension, and you understand why the 2 dimension is very special, it's very easy to fix this situation, right? Because I know that the rows are monotone, I can pick, say, only these red ones, which are monotone the same way, and there would be at least half of them, right? Because you have 2 states, 0, 1. Either it's increasing or decreasing. So at least half of these rows are monotone the same way. And also at least half of the columns are monotone the same way. And therefore from here you can easily get to the array, which is n by n and monotone. And that would complete the proof of the 2 dimensions. Right? So this gives you all the details, more or less. Now let's talk what you have to do, right, to go to higher dimensions. Actually, so this thing which we got in the intermediate step, a 2 by n by 2 by n array, whose rows are monotone and columns are monotone, but not necessarily the same way, will play a role now. Let me call this inconsistently monotone array. So I will write you a definition so that you will be able to remember this. So definition, array is inconsistently monotone if one-dimensional arrays are monotone. So similarly to the equation of Fishburn and Graham, we can denote m prime dn. It's a minimal n such that every n times n d-dimensional array has n times n inconsistently monotone subarray. Right, so what I first showed you is that if you take your big N to be 2 to the 2 to the 2n, then I can find inside inconsistently monotone subarray of size 2n, and then I could use it to get actually a monotone subarray. Now, you can do the same proof, and that I will not do on the board, but that's not very difficult to generalize. You can do this proof, which I did, right, up to this level without the last step, for more dimensions than 2 by induction and some kind of arguments, but you don't need too many new ideas, to show the following theorem. Right, so here it's that m prime d is at most, so let me use it here, maybe letter m, so that we will distinguish it between, like I will later want to substitute something for m. So m times d of m is at most 2 to the 2 to the m to the d minus 1. So you can get double exponential bound in all dimensions on the Ramsey number if you just want some inconsistently monotone pattern. But you have no control which pattern you get. Just all rows and columns would be monotone. So the approach can be you first find an m by m inconsistently monotone subarray, and then inside you will find a monotone array. Right? So note that our proof in 2 dimensions was just by observing that if you want to find monotone array, it's enough to find inconsistently monotone array of twice bigger. This works in 2 dimensions. Unfortunately, the situation becomes much more complicated the minute you go to 3 dimensions, right? Because you cannot just take this intersection of rows and columns. In 3 dimensions, you actually need in every 2-dimensional case find a square, and then you should be super lucky that they're in the same location, that if you take the intersection, you actually will have an intersection, right? So the losses which you're getting are much, much bigger. But nevertheless, this approach can be made rigorous. So let me tell you what we can prove, and I'll give you some ideas. So the theorem which will give our bounds in higher dimension is the following theorem. That for d at least 3, if you want to find monotone array of size n, you can get it from first finding inconsistently monotone array of size exponential in n to the d minus 1, So you first find inconsistently because of this prime, like monotone array of size exponential in d-1, and then inside you will find a monotone array size. So now if you put this together, right, so if you now plug here, right, your n, as I said, 2 to the bigger of n to the d-1, you get our result, right? You suddenly get triple exponential bounds for all the dimensions. Now let me briefly tell you how one can prove this result, right? So good. So again, so what I want to do, I want to show you, right? So already assuming, right? So the goal is to show that every inconsistently monotone array n times n times n in d dimensions has monotone array n times n if my big N is 2 to some constant n to the d minus 1. So if I show you this, right, I somehow will complete the proof. So now we just thinking about the task. So I give you the array where every direction, right? So now I cannot say row and column because it's really interesting only in high dimensions. So every direction is monotone, but every direction chooses its own bit 0, 1 in what it does. It can be increasing, it can be decreasing. There is completely no correlation between the sides. So to prove this result, we will need a very simple lemma, which is usual Ramsey theoretic lemma. So this is a lemma about the colorings of grid. And then I'll use this lemma to do the reduction. And again, reduction is very simple. It's a couple of lines, but somehow it took us quite a couple of months to notice this couple of lines. So what is a lemma? So here is a Ramsey theoretic lemma. And I'll say a few words how to prove it, but it's not difficult. So imagine you start with n being 2 to some constant n to the d minus 1, since this c is large enough. It's a constant, large constant. And then suppose we have a coloring, right? Given k coloring of vertices of d-dimensional, like n dot cross cross cross. So if we color the vertices, or we color, right, so now there are no numbers, we just color the grid, the d-dimensional grid n times n by k colors, then it has n cross cross n monochromatic subarray. So this is a lemma. So it's not very difficult to prove. It's pretty standard. Think about 2 dimensions, right? Suppose you want to prove this 2 dimensions. Then you do exactly as I did before, right? So here is your grid, right? So you go first column by column, and because there are only k colors, so in one column, you will find a subset of size n over k, which is monochromatic. So actually you don't take n over k, you find, right, as long as n over k bigger than n, you find a subset of size n here, which is monochromatic. And you do it in every column. And then again, because here there's n, the n is big, much bigger than n, it's long, so you will have many repeated locations. And you have only k colors. So if the number of locations which you have is more than k times n, there would be n times the same location and the same color. And this obviously gives you 2x2 monochromatic subgrid. And then you can do this in many dimensions, right? So you will have these guys repeated. Let's call it again Ri. So Ri would be repeated many times, right? And many means just more than k times n. This would be already enough, right? And then you get this lemma. So this lemma is not very difficult. So the interesting thing would be to apply this lemma to deduce, right? You see already the similarity of the numbers, right? This number and this number is the same. So the interesting thing would be to apply this lemma, and there is a very simple derivation, but as I said, it took us some time to notice. Like again, I'm making this parallel in Ramsey. You type questions, you many times look on the question, since the number of tools which you have in your disposal is quite limited, right? It looks obvious, but you cannot make the next step until you really see that it's obvious, right? So I want to persuade you that in this case, this can be done. So I want to prove this theorem. So I have this lemma, and I have n by n monotone array, but inconsistently monotone array. And I now want to find inside a really monotone, consistently monotone subarray. So what do? You color this your n by n array in k, which is a 2 to the d colors. Right? So since dimension is fixed, exponential in the dimension is also a constant. And I tell you how you color, right? So you have this inconsistently monotone array. So you take a point in this array, so since this is a point, and you look from x in all possible directions. You go to the left, forward, and up, let's say in 3 dimensions, because I can only draw you 3 dimensions, right? So you look 3 dimensions, right? And you look in each dimension, are you increasing or decreasing, right? Because you know that on every one-dimensional thing, you have a bit, right? Either you're increasing or decreasing. So you pick a point x, and you look in all the directions, and you record color of x is A1, A2, A3, right? I obviously do it only in some, an example is the dimension 3, but it's very easily you will see that it's generalizable. I color this point with A1, A2, A3, and then AI is 0 if in direction I you're increasing. And 1 otherwise if you decrease it. So that's all. Now think what this lemma tells you, right? This lemma tells you that you can find, let's again draw in 3 dimensions by this lemma. Right? You can find n by n grid, right? Such that color of x is the same. Now what does it mean it's the same? It means that from any point x, if you look in all 3 dimensions, you have the same behavior. So now you know that in every direction you either simultaneously increasing or decreasing, because that was the coloring, right? Your coloring told you if I'm in the point x and I look in the direction of coordinate z, if I'm increasing and decreasing. If it's the same for all x, it means for all the direction in the direction z, I have the same behavior as the increasing or decreasing. So this kind of lemma tells you that if you have an inconsistent monotone array of exponential size, you get a monotone array of size. And as I said, right, before for inconsistently monotone arrays we had double exponential bound, and now by adding this thing on top of it, we get at most triple exponential bound. Right? So we have a triple exponential bound starting with dimension 4. We have relatively simple double exponential bound in dimension 2. We have additional tricks which allow us to get double exponential bound in dimension 3 as well, but somehow this does not. Okay. So this was the first batch of the results. Now let me move to another kind of notion of monotonicity, which was also proposed by Fishburn and Graham. Now I want to strengthen the notion of monotone array, right? So remember, monotone array means, let's do it even in 2 dimensions. I will not go much more than 2 dimensions now. So we want all rows to be monotone the same way, all columns monotone the same way. So think about, here is your array, which is monotone. Now, if you take 2 squares, right, which in the same column, then you know their relative situation, right? Because you knew in the columns you are either increasing or decreasing. The same if you take 2 squares in the same row, again you know their relative. You know what happens with the numbers inside because you know every row was either increasing or decreasing. But you completely have no clue if I look on these 2 squares, which are not in the same row and not in the same column. I cannot tell what's going on, even if I know that all rows, let's say, increasing, and all columns, let's for simplicity say all rows increasing and all columns increasing, I still cannot tell you anything. And therefore, Graham and Fishburn and Graham proposed to look on something called Lex monotone, right? So this would be a strengthening. Lex for lexicographic, Lex monotone. So idea is that I want an array where just from sheer location of 2 squares, I can tell you which one has the bigger number, right? So I really have in some sense a kind of ordering over all elements, which I can tell this ordering, right? Obviously, you always have total ordering on the numbers, but I want to be able to tell you this total ordering just by looking on the coordinates. So let me give you an example. So here is an example. So here is one array. 7, 4, 1, 8, 5, 2, 3, 6, 9. So this is an example of monotone, Lex monotone array. And what I mean by this, so you start with so this array, you can see how it builds. You start with the first row in the increasing order. Then you jump to the second row, which is higher than the first row, and it's again in increasing order. Then you jump to the third row, which is again higher than the first row. And also the third row is increasing order. So basically, in this array, if you tell me that you have your second, or doesn't matter, your first coordinate bigger than my first coordinate, that you higher. If you have your second, if your first 2 coordinates are equal, but your second coordinate is bigger than my second coordinate, you again bigger, right? So I really, by just looking on your location, right? In other words, it's basically I took a monotone array and I just filled my square. So obviously, you don't necessarily only need to do it like that. So here is an example, another example. Right, so let me give you another example of Lex monotone array. So now this array again, right? It's not just monotone, but you can first go in first column, you have increasing order, then you jump to the second column, and again, you have second column is bigger than the first column, and it stands in increasing order, and the same thing with the third column, right? So this is, and obviously not necessarily only with increasing, you can do it with decreasing. So now, right, for people, obviously, many people in combinatorics know what is a Lex monotone or Lex ordering is, but let me give you a formal definition. Right, so when I call my array Lex monotone, so obviously it should be monotone, but I want to say the following, right? So if I allow you, so array is Lex monotone, if we can order the coordinates, but not necessarily the first coordinate would be the most significant one, right? It's like ordering the bits. We can order the coordinates, decide which coordinate the most significant one, the next significant one, and so on. We can order coordinates and reflect array along some directions. So for example, in some direction I was decreasing, let me reflect it, let me flip the ordering and I change the ordering of the number so I can reflect arrays along some direction to get total order by coordinates, right? What I mean by total order by coordinates, so once I permute my coordinates and I reflect, I will be totally monotone based on my coordinates. So if you want two squares and you want to compare them, you compare first their first coordinates. If I have my first coordinates higher than yours, I'm already bigger than you. If our first coordinates are equal, then I will compare our second coordinates and so on. So I basically look on the first coordinates in which we differ. And if my coordinates is higher than yours, then I have a bigger number, right? So you are Lex monotone if, right, so it's basically, right, let's do in 3 dimensions, Aij is bigger than I prime, J prime, K prime, if I bigger than I prime, or I equals to I prime, but J bigger than J prime, or right, I equals I prime, J equals J prime, but K bigger than K prime. And it's exactly what you would expect. Right? So Lex monotone means I allow you to decide which coordinate first, which coordinate second, which coordinate third. Obviously, I have to do this because I can build my array by putting actually bigger numbers in the second coordinates and so on. So I should allow you to decide in which order you process coordinates. Then you might be, because you're monotone, you might be in some places decreasing. I should allow you to flip this. And then after that, I get everything increasing, and this increasing is based on the just order of the coordinates. So these are the examples. So obviously, Lex monotone, it's a much stronger property. So again, following this, let's define a corresponding Ramsey function, right? So LDN is a minimum n such that any d-dimensional n times n times n array has Lex monotone n times n subarray. So this is another function which Graham and Fishburn looked at. And obviously should go faster than MD of n because you're getting much more input about how your array looks. So the first question which they ask, right, is this finite? Right? Actually, can we at all guarantee always to find Lex monotone subarray, right? Big subarray, because this is a much stronger property. And the answer is yes. And they showed this function. They also managed to show that the bound for this function is that it's finite. Now, let me propose you some very natural, right? This is actually, they already wrote in their paper, approach how to bound this function, right? We already saw it, right? You don't immediately try to get an X monotone array, but you first start with arbitrary array. Then you already get monotone because we know how to do this. And maybe once you have a monotone array, you try to see if inside monotone array you can find, by paying again something in size, Lex monotone subarray. Obviously, by no means I claim that you cannot bypass monotone and get something better, but that's definitely one approach which they took and we took as well. And to make this approach quantitative, again, let me define you this intermediate function which allows you to do this step. So this would be my function f. So let me define f d of n. It's a minimal n such that any monotone. So if I already tell you that all your directions are monotone, the same way, but maybe some columns are up, rows going down. So any monotone n times n d-dimensional array has Lex monotone n times n subarray. So I know how much I paid here. So for example, think about d equals 2. So if in d equals 2, I know that here I pay double exponential. Loss. And the question to go from monotone to Lex monotone, how much I pay. And this is my quantity, right? So my kind of a result, which it's not a, right? It's just tautology from my definition, is that LD of n is at most MD of FD of n. Right? So I first get a monotone array of this side, and then inside it I find the Lex monotone. And now to complete, let me tell you what is known about this function, what they proved and what we managed to prove, because we have a pretty substantial improvement here as well. Right? So bounds. So actually they have a very, very nice argument which we managed to make absolutely tight and refined, which shows that f2 of n, right? So if you do it in 2 dimensions, you just don't lose much, right? So in 2 dimensions, you already pay here double exponential. Here you just lose quadratic. So if you have a monotone array of order constant and square, you can find inside a Lex monotone array of order n. This is a very nice argument. We know how to refine it. We actually know the complete answer here. So we actually know what this function is. Right? So it's 2n squared minus some error. But they really were paying a lot if you go for D, which is bigger than it, right? So they managed to show that in order to get a Lex monotone array of size n, you need to start with an array whose size is a tower of D of size n, right? So it means for 3 dimensions, it's exponential, for 4 dimensions, it's double exponential, and so on. So that was there. So. And so our new theorem, yeah, so it's a G that we managed to reduce significantly this for dimension bigger than 2. So we show that for every D bigger than or equal than 3, this FDN is at most exponential, is at most 2 to the n to the d minus. So if you want to get a Lex monotone array, just take a monotone array of exponential size in n d minus 1, and then inside you can find a Lex monotone array. And therefore, as a corollary, right? We will get the bound for this function. So if you want to find a Lex monotone array, right, you need at most 4 exponentials. So it's x, n to the d minus 1 or minus 2, right? Something like that. So at least at most 4 exponential upper bound instead of Ackerman. Again, it's much right, it's much more much smaller bound you need here to get the result. So that's quite involved. I will not be talking about this. Just want to mention because it's a very interesting monotonicity notion, very strong, and you still can get it. Now, to conclude, let me mention some open problems which I think we like the most. So here are the open problems which I want to mention. Right? I maybe delete this. And I write what we want to do. So first of all, right, if you want just two-dimensional n by n monotone array, right? We showed that it's double exponential, right? Right. So we know double exponential and it's at least exponential. So it would be very interesting to decide which way you go. Do you really need double exponential or not? Right? So our proof was pretty simple, but as I said, it's all misleading. Our simple proofs, it took us some long time to get it. But it's not clear, right? It seems that we're already squeezing everything. We didn't see what else we can do. Now, again, it seems for us, right, that if we manage to do it, right, if we only could have do double exponential in 2 dimensions, we would think that maybe it's artifact of dimension 2. But we also managed to get a double exponential bound in 3 dimensions. So this for us strongly suggests that maybe you should get double exponential bound in all dimensions. We didn't find such an argument, but probably, right, it's probably true. And now the last thing which I mentioned in the very end, FDF. Right? So again, so you remember what it was. It was if I give you already big array which is monotone, I want to find a subarray which is Lex monotone. Right? We showed here an exponential bound. But the lower bound is only polynomial. Right? And we know that for d equals 2, it is polynomial. So again, it would be very interesting to decide, right? If I want to go for the strong property, Lex monotone, I have already monotone array. Do I really need to lose extra exponential? Right? This would be again a very nice, but by itself a very nice problem. Right? So I give you already that, you know, in every direction you're increasing or decreasing. Think for simplicity, for every direction you're increasing because I can only always flip the ordering, right? But I want to be Lex monotone, right? I would be want to have this stronger property. Do I need to lose exponential or polynomial in the size of the array? And I think it's 3 very nice problems. I would not be surprised that you can have an extra observation which kill one of them or all of them. And I leave you with this problem. Thank you.
Thank you very much, Benny, for a really beautiful talk. I'm sure I'm not the only person sitting here who envies you your blackboard. Could you please let me know if you would like to ask questions either in the chat or by raising your hand. I'll get things started by asking a question myself. So in your last section, you had this sort of 2-step proof where you went via the monotone array firstly. Do you think there's something that could potentially be gained by bypassing the middle step and going straight to lexicographically monotone?
Absolutely, right? As I said, there is no inherent reason why you cannot go directly to Lex monotone. so having already monotone array make it simpler. And also, I think this was a mind of, I cannot talk for them, but this was a mind of Graham and Fishburn, because they probably first got that in 2 dimensions you lose almost nothing, right? You just a polynomial factor. So if you would have always lose only a polynomial factor, this is an amazing argument. So they lost a lot. We managed to reduce it to single exponential, but maybe you don't lose at all. Then it would be a nice avenue, but potentially you can bypass it. We try. I don't see how to do this.
Thank you. Is there anybody else who would like to ask a question? Alex, would you like to unmute yourself and ask?
Yeah, so Benny, thanks for a lovely talk. For the 2-dimensional case, do you have a sense of which is more likely to be true, the single or double exponential? Which do you believe?
Not really, right? I mean, we tried. We will basically had even and odd days, right? When you think that one is true and another is true, and as I said, right, this whole process working on this paper showed us why the Ramsey theory is so hard, right? You have something which you completely have no idea how to improve, and then the next day you have some idea, and then you say, my God, look, you can start with even original thing, right? Right, unless you go to the paper of Graham and Fishburn, try to imagine how for these 2 dimensions they get power of 5, right? But you can easily get power of 5 if you do your first probe. So it can be easily that it's exponential, but it can be also that it's doubly exponential, just because we know that for hypergraph, and maybe arrays are a little bit like hypergraph, the random constructions are not necessarily the best. You have some maybe clever stepping up procedure which allows you to do combine random with something else. So I really don't want to speculate here. It's really very interesting question. What I probably more would believe that for 3 dimensions and further up, you should get double exponential, and we just don't see how.
Thank you very much. I can't see any other questions either in the chat or in raised hands, so I think we're going to draw to a close there. Before we unmute everybody and thank Benny in the traditional manner, let me just say that next week we have another one of our special thematic days, with the theme being logic and combinatorics. We have talks from Tamar Ziegler and Anand Pillai, and we hope to see many of you there for that. So it just remains for me to press stop.